Griffiths E&M section 5.1.3 currents part 3, the continuity equation. So previously we have discussed that there is a current that we can calculate, and that current comes in a number of different flavors, one of which is the volume current density, J. I can write the current going through the current carried in a wire by integrating over a surface where I have my volume current density going through some perpendicular surface, right? That is some cylinder. I have some patch on here, and this is the current going through that patch. The current density going through that patch. I can go ahead and rewrite this as a dot product because the current is going perpendicularly through the surface. So that is J dotted with dA. And that's integrated over this entire surface. Okay. We can rewrite that using the divergence theorem as the integral over our volume, if that surface is closed, of the divergence of our current density over that volume. Okay, so I have some not wire, some three-dimensional volume. I can calculate the current going through these surfaces, and if I do that over the whole surface, that can be represented by the divergence theorem. So the divergence of that current density is also equal to that. So let's think more about what this divergence represents. So over the whole volume, I have a divergence of my current density added all up over d tau. So in space, if I have some current density that looks like this, that is going to have a non-zero divergence. And that non-zero divergence is going to say that is going to lead to current leaving this area. So in the end, this region of space will have less charge than the other places. Okay. So if I have a non-zero divergence of my current, that means that my total charge in my region of space, which can be calculated by integrating over that charge density, is changing in time. Okay. Technically, there's a negative sign there that tells you that outward flow results in the decrease of the charge that remains. Okay. I can rewrite this as, I can take that time derivative inside and say that charge density changes with time, and you rate that over our volume. And that is equal still to the divergence of our current density added up. Now these are both volume integrals over the same volume, and therefore it holds for any volume that the divergence of our current density is equal to negative the change in the charge density with respect to time. This is called the continuity equation. Basically, if I have some distribution of charges, I'll do this in 1D for visuals, and my flow field is not uniform, then over time, I will accumulate charges, something like this. and that will change the charge density.